Thank you to the organizers for asking me to speak to this audience, which is always a pleasure. But initially, Subhro said that I should try to speak on localization. But then I thought, okay, instead of giving an overview of many-body localization, it's actually much more exciting to speak and to probably hear about something which we have been doing more recently. And then I'll sort of, there is a localization component to it, but I'll get to it probably towards the end of the talk. And Mohit also asked me that, I should try to pitch in at least the first part of my talk at a colloquium level. So I will try to do that. I mean, I'll set up a slightly general framework. And as you'll see, this stuff about logarithmic light cones in MBL will sort of be an application of this framework. Okay, before I start, let me say that some of the details of what I'm going to talk about can be found in these 3 papers, which sort of was done mostly by Vikram Pine and Ratul Thakur, graduate students in my group. And yeah, I think if you have any hard questions, at least Vikram, I saw Vikram in the audience, so you can, of course, ask them. Okay, so eigenstate correlations. Now, at this stage, it might seem like a slightly cryptic word, but let me just say how we ended up thinking about this, and then I'll explain what are we actually thinking about. So it turns out that we were parallelly thinking about 2 seemingly different questions, both of which, or we realized that the answers to both those questions actually sort of were hidden in what we call eigenstate correlations. So the first question that we were thinking about was had to do with chaotic quantum many-body systems. So these are isolated chaotic quantum many-body systems. I think Shivaji gave a sort of glimpse into the kind of things that one might be thinking about: random circuits, low-k systems, or systems, systems which are far out of equilibrium. So most of the things that we learn in a condensed matter theory course, or many-body theory course, is not really applicable. But then, of course, that doesn't mean that we don't make any progress. So there was a lot of progress in understanding chaotic quantum many-body systems. And one of the key insights into all of this was that the universal properties of the spectrum of these systems was very well described by random matrix theory. Now, you see, at this stage, I'm already talking about the spectrum. So I'm not talking about ground states or low-lying states, which we are usually confined to thinking about in the context of condensed matter theory. And so I'm sort of talking about states which are majorly in the middle of the spectrum. So then it was realized that a lot of the things like level repulsion, even quantitative things like Wigner-Dyson statistics of the level spacings can actually be described by random matrix theory. And it was quite tempting to say that, well, okay, sort of generic chaotic quantum many-body system is essentially a random matrix system. But you think for 30 more seconds and you realize that cannot be the full story, because in a random matrix Hamiltonian or in a random matrix, there is absolutely no notion of locality. However, we like to believe that most of the physical systems that we are dealing with have locality in them. The interactions are local. So where is that information hidden? For example, if you compute the spectral form factor, there is a Thouless time, which is, roughly speaking, the time at which the system realizes that it's locally interacting, and beyond this time scale, it sort of forgets that it's locally interacting and starts behaving like a random matrix. Even more importantly, you can have spatiotemporal structure of quantum correlations. We talk about the butterfly effect. We talk about entanglement velocity. So we say that, well, yes, if you have chaos, you do something here, this proverbial example of a butterfly flapping its wings here and something else happening in a different part of the world. But of course, this does not happen immediately under local interactions. There is a finite velocity with which this perturbation is going to travel. And that again means that there are notions of locality in the kind of chaotic quantum many-body systems that we want to think about. But where are those hidden? Where is the spatiotemporal information hidden in the eigenvalues and eigenstates? So this was one question that we had been thinking about. In parallel, there was another question we were thinking about, which had to do with many-body localized systems. So these are, again, out of equilibrium quantum systems, which are interacting, but also very strongly disordered. And what the disorder does, and again, Shivaji spoke about rediscovering MBL. So one thing that sort of is a hallmark of these systems is the fact that they evade thermalization. They evade thermalization, and therefore they fall out of the usual paradigm of statistical mechanics, which is why I think they're worth discovering and rediscovering and asking questions about what leads to MBL and so on. Now, the point is there is no charge transport in these systems. That's why they are localized. They're interacting insulators if you want. But the key point is, even though there is no charge transport, there is information transport. And that happens due to what we call dephasing. That's not important at this stage, but the key point is that there is information transport. And you see the signatures of this information transport, although anomalously slow, in the fact that if you compute a quantum information measured like entanglement, or some information scrambling measured like out-of-time ordered correlators, you see them to be logarithmically slow. The light cone is logarithmically slow, and so on and so forth. So then, of course, this is not new. This was known since 2012 by a very important work by Jens Badersen, Frank Polman, and Joel Moore, when they were all in Berkeley. But then, this was understood for a long time via a very phenomenological, borderline hand-wavy argument saying that, well, many-body localized systems basically are dressed versions of a classical system, and this dressing is exponentially decaying in space. And if you have something exponentially decaying space, you have something which is logarithmically slow in space-time. So we said, okay, this is not something that can be explicitly testable, because it's very hard to construct these dressed degrees of freedom, which are supposed to be conserved under many-body localized dynamics. And in fact, there is no unique way of constructing them as well, as far as I know. There are various things you can try to do and construct them approximately. But as far as we understand, there is no explicit way of constructing them. Of course, you can make a lot of progress by assuming that they exist, and then you can go ahead with that. But this tells me that, or this told us, that it will be nice to have a microscopic theory which is devoid of these dressed local or quasi-local degrees of freedom that would explain this logarithmically slow growth of entanglement. So we thought about this for a year and a half, and it turned out that the answers to both these questions actually lay in what we called minimally 4-point correlations in eigenstate amplitudes. Okay? So with this motivation, let me try to say, what do I mean by eigenstate amplitudes? Okay, so the first thing is, as I said, when we talk about these isolated quantum many-body systems which are thermalizing, what we typically want to think about are local degrees of freedom. And the way these things, or the way statistical mechanics or equilibrium statistical mechanics emerges in these settings is that for a very small subsystem, the rest of the system, which is much bigger than that subsystem, essentially acts like a bath. The temperature is set by the initial condition, and so on and so forth. And you sort of say that, well, okay, at late times, local observables in this small subsystem would behave as if they were in a Gibbs ensemble described by the temperature set by the initial state. And that's an extremely loaded statement. And of course, that's why this was formalized under this, again, a very sort of cornerstone concept in this field, which is called the eigenstate thermalization hypothesis. And what it does is it sort of gives you a statistical statement about the matrix elements of local observables in the eigenbasis. Now, at this stage, I don't want you to sort of focus on the exact form, but what I want you to focus on is that this is precisely a statement about the matrix elements in a pair of eigenstates and nothing more. It does not make any precise statement about how these random variables Rmn might be correlated. Okay, and this is something that's going to play a rather crucial role. And what this is very good at doing is, first of all, it's very good at predicting what will be the infinite time behavior of this, because the infinite time behavior is going to be thermal, and that's actually what anyway this sort of sought to do. So as far as that is concerned, you cannot sort of blame the ETH. The ETH was not designed to tell you what the spatio-temporal dynamics of local observables or information would be. So that just tells me that there is more to this question than just ETH. Now, another thing that you realize is that if this has to happen, that if the rest of the system has to act as a bath for this, then there has to, and I'm saying this in a very sort of loose colloquial way, is that this has to have a lot of quantum correlations across the system. Now, this subsystem is not special. It's true for any subsystem. So what do I mean by saying that, well, there should be a lot of quantum correlations? What I actually mean is it's not sufficient. It can happen that 2-point correlations actually go to 0, simply because the state is sort of sufficiently structureless. However, there should be sharing of information between these different parts of the system, which means that there should be multi-party correlations between these different parts of the system, which can be encoded in the entanglement. So thermalization goes hand in hand with the growth of entanglement in the system. That's sort of the main message of this slide. Okay, and the other important message was that ETH at this stage is just a statement about matrix elements in sort of pairs of between pairs of eigenstates. So that's fine. And as I said, we will be interested in local Hamiltonians of this kind. But this locality of the dynamics is manifestly beyond random matrix theory, as I sort of alluded to in the very beginning of my talk. Because the locality of the interactions gives you a bound on the maximal velocity of information scrambling. And this was known since, again, a very important work by Lieb and Robinson from 1972, where they derived a bound saying that if the interaction is local, then perturbations can only spread at best with a finite velocity. Now, again, this thing is not restricted to local Hamiltonians. You can also think about random quantum circuits, which again have a local structure in the sense that the gates that make up the circuit act only between nearest neighbor qubits. And in fact, in the recent years, a lot of us have preferred to think about this problem in the context of these circuits and not in the context of Hamiltonians, simply because they're easier to solve. Again, I think this is something that Shivaji had mentioned in his talk. And one thing that's made very explicit by these kinds of settings, by the way, you can take a Hamiltonian and you can always trotterize it and write it like this. So is that there is a very distinct sharp light cone, simply because how the gates are arranged. And this was sort of the main idea of Lieb and Robinson, and there's been a flurry of works on talks in these random circuits. And I didn't even try citing any of them because I was certain to miss out on a few. So I thought I'll not cite any of them. Okay, so the point is that there is this locality, and where is this hidden in the eigenstates? So that sort of sets out the important questions that we actually wanted to answer, which is how is the notion of locality encoded in the eigenstates, and what features of eigenstates are not captured by random matrix theory. And then you can talk about what exactly are the eigenstate correlations you want to be looking at, and then there are connections to conventional measures of information scrambling and so on. Now, at this stage, let me say one thing, that why are we talking about minimal eigenstate correlations? That's because if you give me all the eigenvalues and all the eigenstates of the system, or even if you give me an ansatz or a statement about the joint distribution of all these numbers, I can, of course, in a statistical sense, reconstruct every dynamical quantity that you can think of. But that's useless because the Hilbert space dimension is exponentially large in my system size. The eigenvectors are exponentially large vectors. The number of eigenvalues is exponentially large. So that's basically too much information to be useful. So that's why we want to sort of think about the minimal correlations that will actually encode this notion of spatiotemporal information scrambling. Okay, so first let's pin down a quantity that we'll use to think about information scrambling. And we don't want our diagnostics to depend on which operators you chose, because suppose I give you the out-of-time ordered correlator between sigma z here and sigma x there. Someone can say that, oh, how do you know that one of these operators does not have an overlap with some conserved quantity in your system? And what happens if you change the operators? What happens if you sort of take slightly different operators, and so on and so forth? So what we first wanted was an operator-independent definition of spatiotemporal scrambling. And remember, our original motivation was to talk about statistical properties of eigenvalues and eigenstates. So we just want to work with the time evolution operator. So what we'll actually work with is the entanglement properties of the time evolution operator itself. So the way this works is normally, we are used to thinking about states acting on n qubits. But then under that notation, any operator can be written in this way. It takes an n qubit state as an output and takes out or gives out an n qubit state, as an output, yeah. But I don't have to think about it in this way. I can always think about it as a state on a doubled Hilbert space on 2n qubits modulo some normalization. And that's an exact mapping I can always do. I can do it for any operator, so I might as well do it for the time evolution operator. So you would normally write the time evolution operator in this way. All I'm doing is writing it in this way. This is, I mean, it goes under the name of Choi-Zamolkowski isomorphism and so on, but I'm just saying that this is an exact statement. There is nothing I'm sweeping under the rug here. But now that I have this, given that this is a state on 2n qubits, I can take any two subsystems and I can ask for the mutual information or entanglement properties between those two subsystems. More importantly, the two subsystems that I'm interested in can be at two different times, and therefore, and can also be sort of separated in space. So I have basically the mutual information of between two subsystems, one of which, remember, this blue one, x was at time t equal to 0, this red one, y was at time t equal to t, and they were spatially separated. So what I can always do is I can compute some notion of mutual information. Now, to the quantum information experts in this audience, they might say that this is not a very good quantity because the mutual information defined in terms of second-Renyi entropies violates all kinds of monotones that conventional measures of entanglement or well-defined measures of entanglement should do. If I wanted to be mathematically rigorous, what I should have done is I should have replaced these with the von Neumann entropies. But that's harder to calculate. Taking averages of logs is very hard. So we stick to this. Numerically, we find the same phenomenology for von Neumann entropies and for any entropies. Okay, so that's the quantity that we are interested in. Now, just to give a flavor of why this quantity works, think about this time evolution operator written as a state in this way. And let's imagine I'm at time t equal to 0. So if I'm at time t equal to 0, then the time evolution operator is nothing but a direct product of identities on different sites. But if I now unfold that identity into an operator, into a state, it looks like this, which is nothing but a triplet state. And triplet is a Bell state. So obviously, this degree of freedom is entangled or maximally entangled with this degree of freedom and so on and so forth. If I now take a cut like this and I ask for the operator entanglement between the red degrees of freedom and the black degrees of freedom, I will exactly get log 2 times the number of such bonds I cut. And in this case, it's 2. Now, suppose time has evolved. This is no longer identity. As I said, there's a finite Lieb-Robinson velocity. So what should happen is that these qubits now get entangled with their neighbors. And if I now cut a line, then of course, the Bell pair picture does not work anymore. But nevertheless, what you can see is qubits within this sort of shaded rectangle are actually entangled with each other. So I now have to start cutting more and more degrees of freedom or more and more entangled degrees of freedom to compute the operator entanglement between the same red degrees of freedom and the black degrees of freedom. So what that means is at time t equal to 0, the entanglement profile looked like this. But as time progresses, the entanglement actually grows in this way. But one important thing is if you are at some finite value of L, which is how sort of a measure of how tilted your cut is, you can see that it starts deviating from its time t equal to 0 value at a later and later time. And that's just the manifestation of the fact that there's a finite velocity with which entanglement can propagate. Okay, so what I wanted to convince you of here is that this operator entanglement is a good quantity to look at. And now let's come back to this issue of eigenstate correlations, or this operator mutual information and eigenstate correlations. So you look at this and you immediately realize a bunch of things. The first thing is that the second Renyi entropy, which is defined in this way, involves 2 factors of U and 2 factors of U dagger. So that automatically tells you that to compute or to do anything to do with this operator entropy or operator entanglement entropy or operator mutual information, you need 4 factors of U's and U daggers. So you definitely know, if you write them in terms of their eigenstates, you definitely need 4 eigenstates minimally. That's the minimum you need. And you see that already sort of goes beyond what ETH was going to tell you, because ETH, as I kept reminding you, was a statement about pairs of eigenstates. And then, of course, you need these things to be gauge invariant. And the last important point is that these must encode the notion of locality in terms of where the subsystems X and Y are. So now in the rest, in the next 2-3 minutes, what I'll try to do is I'll try to construct an appropriate eigenstate correlation which satisfies all of this. Okay, so in order to do that, what I do is I say, okay, I have my time evolution operator. These alphas are my eigenstates, theta alphas are the eigenphases, and so on and so forth. So the first thing I do is, remember I wanted this x, which was the subsystem, to appear. So I take the state, and instead of writing it as a vector, I write it as a rank 2 tensor by splitting it like this. If I did an SVD of this matrix, it would have been the Schmidt decomposition. But at this stage, I'm actually not interested in the Schmidt decomposition. I'm just sort of writing a notation whereby the state has now been written as a rank 2 tensor. It can, you can also think of it as a matrix which has dimensions of the Hilbert space dimension of x times the Hilbert space dimension of x bar. Okay, now let's try to construct scalars from this. So if you give me two eigenstates, the only gauge invariant scalar I can construct is this quantity beta alpha. I have to contract x and x bar because that's how I can sort of construct scalars from higher rank tensors, and that's just the trivial orthonormality of eigenstates. There is nothing to do there. If you give me 4 eigenstates, now actually I can do something non-trivial. I can actually construct a diagram which looks like this, where these different eigenstates are contracted on the two different subsystems. Okay, so that's sort of is how you construct this 4-point function. And if you want to, if you don't like these diagrams, if you want to write it in terms of matrices, that's what it looks like. It's a trace of this matrix. And so we have an eigenstate correlation. It is, of course, basis invariant. It's not yet gauge invariant because I can put arbitrary phases to the eigenstates, and that will show up in the phases outside. It has the information of x, which is the subsystem, and it involves 4 eigenstates. Now, even though this is not gauge invariant, v of x times v of y star is necessarily gauge invariant. So now you see I've constructed a quantity which takes into account 4 eigenstates, has the information of a subsystem x and the subsystem of y, is basis and gauge invariant. So it has satisfied everything that we had originally wanted it to satisfy. And it turns out that you can define a 4-point eigenstate correlation, which is v of x, v of y, and now because you have 4 eigenstates, you need 4 eigenvalues. Normally, we are used to thinking about sort of, when you think about dynamical response, we think of a single frequency, which is the difference of 2 eigenvalues. Here, of course, there are 4 eigenvalues, simply because I had 4 eigenstates to start with. And the very nice thing is, and of course, you can see that I'm not presenting it chronologically in the way we thought about it. Of course, we did it the other way around. We wrote down the operator mutual information, and we said, okay, what eigenstate correlation does it correspond to? And then we realized why this eigenstate correlation keeps appearing everywhere. And the reason is that you can write down the operator mutual information exactly in terms of this 4-point eigenstate correlation. You can write down the operator entanglement entropy in terms of this eigenstate correlation. Now, so therefore, we have started answering some of these questions. We need minimally 4-point dynamical eigenstate correlations. This correlations, if you compute for a chaotic system, is going to be completely different from a random matrix, because a random matrix has no notion of locality. What is the diagnostic? The diagnostic is operator mutual information. What is the analytical form of the eigenstate correlations? It's this. The last thing that would be nice to have, just to close, just to tie up some threads, is are there measures? Are these connected to conventional measures of information scrambling? And the answer is actually yes. So what I can do is I can take 2 separate subsystems. I can compute the out-of-time ordered correlator between an operator OX, which is supported at X, and an operator which is OI supported at Y. That's how you define the out-of-time ordered correlator. This is out-of-time ordered because you see this is at time t, this is at 0, this is at time t, this is at 0, and so on. And then we did something very naive and very stupid. We said we don't want the dependence on operators, so let's just average over all possible operators which have support on X and Y. So we did that, and if you do that, you see that this OTOC can again be written in terms of that same eigenstate correlation that I defined in the previous slide. In fact, it's not just OTOCs. You can also, so yeah, this is what I was saying, that these OTOCs can be written in terms of the operator purity now. In fact, not just 2-point functions, sorry, not just 4-point OTOCs, I can also do 2-point functions. Except then, if I want to look at 2-point functions, I have to change the locality of the eigenstate correlations that I do. So I'll not go through the details of this. Let me just summarize it actually in this diagram. So suppose I have these eigenstate correlations which I defined as fxy, but of course if I can define an eigenstate correlation fxy, I can define it also for fxy bar. If these subsystems are local, you can relate them to autocs or to two-point functions. If these subsystems are non-local, again, which you can do, you can relate them to the operator entanglement entropy or to the operator mutual information. So that I hope, that's the first part of my talk where, and this is completely general. I did not make any assumptions about whether the system is chaotic, whether the system is a Hamiltonian system, whether the system is a circuit, or the dimensionality of the system, and so on and so forth. All I said was, if you want to encode the spatiotemporal structure of information scrambling in the eigenstates, it has to be at the level of these 4-point functions. Okay. All right. So I see I have around 8 minutes remaining. HRK, can I get 2-3 more minutes because of that? Good. Okay. So let me now move to this issue of many-body localization. But before I do that, I'll just say that within ergodic systems also, you can actually compute these things exactly for some classes of random unitary circuits, such as dual unitary circuits. And we also managed to do it for Floquet dual unitary circuits, and we could actually show how the light cone emerges and so on. But okay, and this is a topic of an entirely different talk, so I'll not get into that. Okay, so let me now come to many-body localized systems. So I need a specific model. So the specific model that we use is not that specific or not that special. It's just a non-integrable spin chain which is driven, and we chose this because we wanted to write it as a circuit, and that just simplified many of the computations for us. And then there is this disorder here, or there is this competition between the disorder and the quantum fluctuation term given by gamma. And what was shown quite convincingly in a paper was that if you are at gamma, let's say less than 0.3 or something, this model actually, for this sort of system size, is accessible to numerical calculations, sits well inside an MBL phase. Okay. In fact, we said, okay, let's just do some benchmarking in terms of the operator entanglement entropy and so on. So we did all that, and you see this is the light cone of the operator entanglement entropy. Now it looks linear, except notice that time is on log scale here. So that tells you that this is actually a logarithmic light cone of operator entanglement entropy. In fact, what we found was, these are the operator entanglement entropies for different values of these L's, which is sort of this space in the spatiotemporal. And you can collapse this on top of each other if you rescale the time scales rescale the times by a time scale, which again grows exponentially with L. So numerically, this model seems fine. This is a model which has the logarithmic light cone. So we said, okay, let's try to understand why this logarithmic light cone emerges from the point of view of eigenstate correlations. Okay, so remember, and this is just for recollection, that the operator purity, whose log would give us the operator entanglement entropy, is just given by this correlation. And this is the setup that I'll be thinking of in the rest of the talk. What will be more convenient is to write this in the frequency space. But now when I say frequency, I mean the frequency that was defined with respect to these 4 eigenvalues. And if I do that, I'll just get something which looks like this. This delta of 2 pi just means that this is a delta function on the unit circle, because all my eigenphases live on the unit circle. All that means is that 2 pi is identified with 0. Okay, so then, given that we had this, we thought, okay, let us forget about this frequency for the moment. Let's take it step by step and first look at what is the statistics of this curly V, which is nothing but this product. So when we looked at the distribution of these V's over all possible quartets of eigenstates, we found that there is this distribution, and this green is the smallest system size, the blues are the sort of next largest system size, the reds are the largest system sizes, and so on. So we saw that there's this huge peak close to 0, which is essentially not 0, but something which is exponentially small in system size. But then there is an order 1 weight on an exponentially small number of quartets. So now it suggests that it could be that this entire sum is dominated by quartets which live in this region of the probability distribution. So that sort of raised the question that what is the anatomy of these special quartets? And of course, you have to then ask how many of them are there. And then there is a third question, which is what to do with the spectral correlations within these quartets? So those are the three ingredients I need in my theory. Okay, so let's now try to understand these structure of the special quartets. Now, this curly V is made up of a product of these two eigenstate correlations. So remember this diagram, and that's where this diagrammatics actually was useful. This can actually be written in this way. So you add one more ingredient to this picture, which is that the eigenstates are somewhat tightly localized on the Hilbert space. They are not very tightly localized because we know that MBL eigenstates actually show multifractality, and I mean those are details, those are correction terms that can be incorporated into this theory. But the point is, let's just say that they are more or less tightly localized on the Hilbert space. So now if you look at this pair, for example, alpha and beta, they are contracted on 80 bar. So 80 bar is this part. So this is 80, this is A0, if just to sort of remind you of, this is A0, this is 80, this is A0 bar, and this is 80 bar. So alpha and beta, therefore, must be very similar in 80 bar. So now you can start color coding them. So beta and lambda should be very similar. Beta and lambda should be very similar in 80. So that's why they're both yellow. Similarly, these two should be, gamma and lambda should be very similar in 80 bar. So that's why they are green. And then finally, alpha and gamma should be very similar in 80. So that's why both of them are blue. But then let's not forget about the other one. So if you bring in the other one, then you see alpha and gamma, or let's say alpha and beta, have to be very similar in A0 bar, which is this part. Now, this is, sorry, A0 bar. So this is fine. This is already satisfied. But if beta and lambda have to be similar in A0, that just means that this part was same, but this part was not. Remember, this is A0 bar. So this is A0. So if you sort of run through the permutations, you end up with a picture like this. So the parts where the colors are similar means that the states have to be very similar over there. If you do that, then you can do a very, now that I've boiled it down to these colors, it's trivial dimension counting. If you count, you'll see that the number of these quartets exactly scales as nh squared times 2 to the power minus 2l. And then we said, okay, let's scale it like that, and this part immediately collapses, which tells me that there is some merit to this, picture, this construction. So we thought, okay, this works, let's go ahead. And what we said was, let's make a drastic assumption. Let's collapse all of this to 1. Let's say that I don't care what order 1 value it takes. I'll just think of it as some order 1 value. And we ask the question that, can I write it in this way, where I say that I'm going to restrict the sum only over these special quartets and keep the eigenvalue correlations. I've set this to 1 for these. And turns out that I can do that. It looks, it almost reproduces the actual dynamics to very small errors. And then the last thing I need to do is I need to say something about these spectral correlations and their interplay with the spatial correlations. So what we then did was we said, okay, these are the special quartets. Remember that the special quartets were of this form. So this and this is different. Blue and yellow is different. Red and green is different. We said, okay, where are they different? So let's say they're different over a certain length scale, which I call Rx, and I call them Ry. And all I then need is to understand how do these spectral correlations depend on this Rx and Ry. So what we then did was we went ahead and calculated these spectral correlations resolved in Rx and Ry. We got this curve. Now, anyone who has played with data for even for a while will immediately say that, oh, well, this looks sort of eminently scale collapsible. And that's what we did. We scale collapse this data. That actually gave us an energy scale omega star, which scaled exponentially down with R. So that you put together, then you can do this sum, given that you know the scaling form, a saddle point emerges. I'll not get into the details of that. Once you do that, this is the answer that you get. That in frequency space, this operator purity for a given separation has this form where omega L is this characteristic energy scale, which depends exponentially or decays exponentially with L. you can now take the Fourier transform of this, and you get in time domain, you get the purity of this form, which then means that there is this time scale associated with the growth of the operator entanglement entropy, which is that for t much, much less than some scale, which is exponentially small in, or the time scale is exponentially large in L, this has a very slow power law growth, followed by this log t growth, which is characteristic of an MBL system. All these extra corrections actually just show up in a further log-log correction, which of course we have no hope of resolving in experiments. But that's essentially how microscopically the eigenstate correlations actually encode this information of the logarithmic light cone. Okay, I think that's all I wanted to say. So in the first part of the talk, I sort of said, where are the eigenstate correlations, or how do the eigenstate correlations hide the information of spatiotemporal information scrambling? That's basically in these 4-point functions. I did not talk about how you can compute these things in a class of ergodic systems, but I did talk about how in many body localized systems, these things are basically can be thought of as the microscopic origins of this logarithmic light cone. Thank you.
So I might wonder if I've gone to 4-point, maybe there should be things that care about 6-point, 8-point correlations. So you have a sense of what they might be? Can they have to do with kind of unitary K designs, things like that?
Yes. So the reason 4 points sufficed for me was because I was looking at the secondary entropy. If I looked at higher and higher NE entropies, which would then mean looking at higher and higher K-point tau-talks, at least for ergodic systems, actually we are trying to do that calculation. That basically means that if you have these replicas, you write this in terms of these permutations, and then only the non-crossing ones dominate. That basically takes you to this notion of free probabilities, and then you hark back to a paper by Michele Fava and Jorge Kurchan, and you say that, oh, okay, K freeness implies K designs.
I'm trying to understand the connection to a slightly different way of thinking about the correlations. Where, so I mean, I think one could also think of it as having the system split into 2 subsystems, right? And then the thing that there's another locality also implies that there's local conserved quantities in the 2 subsystems. And
if you have conserved quantities to start with.
Indeed. So let's say we have a eigenstate of a Hamiltonian, so it has a conserved energy. And then the sloshing of that energy back and forth between subsystems naturally produces some correlation with the eigenstate.
Yes.
So are these additional correlations beyond that, or is it the same?
So, okay, that's a very good question. In fact, Bikram is the right person because he has been thinking about this question not for Hamiltonians, but for a circuit with U1 symmetry, which is also sort of additive charge. So yes and no. So the reason is, if I go back to the ETH statement, you can actually say that, well, even in a, okay, I don't know, I mean, the ETH statement. In a system without conservation laws, there is still a spatial structure. And therefore, even there, ETH cannot be the full story. Okay, we might not even want to think about it because 2-point functions will decay exponentially in space and time. So, that's all that there is to it. And of course, you can say that if you have conserved quantities, then diffusion is going to kick in. And then where is this information? And indeed, the correlations, or those correlations will be in the correlations of this RMN matrices. So if I take RMN and I take RPQ, then how is RMN RPQ?
I should clarify. I wasn't even thinking about diffusion. I was just saying, if I want to construct an eigenstate at energy E of the full system.
Oh, I see.
I should
okay.
Superpose and E and E that are close.
Yes. So I think, no, so, okay, so you're talking about the ergodic bipartition ansatz. Okay. Yes, these correlations are on top of the ergodic bipartition ansatz. Yeah.
So if you now put back the fact that these states are actually multifractal on the Fock space, so how would it change this thing? And second thing is, how do you see this time scale that you are, I mean, do you see this in the simulation? I mean, like when you look at entanglement entropy growth?
So numerically, okay, so I can answer the second question first because that's easier. These are exact numerics. So this is, these different colors are different values of L, which are different cuts. And you see, for a larger value of L, this takes off at a later and later time. Now this is times in logarithmic scales. So you can actually collapse it by an exponentially large time scale, and they actually all, at least the onset time actually converges. Of course, you don't expect the curve to collapse here because depending on L, you have different broadenings of the entanglement front. So that's why that's something you can actually see here, that larger L has a more gradual upturn, and that's because there the entanglement front has broadened a bit more. So yes, that's how you can see the time scale, that it is in, and also this is a numerical result on whatever 12 sites. So okay. The multifractality part, that of course is slightly harder to, so what we think will happen is, I made this very drastic assumption that I went from here to here. And there I sort of folded in the fact that the quartets that dominate can have order or exactly one contribution, and then the quartets that don't dominate, they actually have an exponentially small contribution, but there are also exponentially large number of them. I sort of threw them away into this bin of 0. So one would actually need to put back that in some bimodal-like distribution and rescale the weights appropriately with the Hilbert space dimension given the multifractal.
Will that give any other energy scale or something?
That we don't know. We didn't do that. We just realized that it can do, and the leading term will be, well, it might actually renormalize. So you see, we got this xi, which was a fitting parameter. So maybe it will renormalize that leading order.
Yeah, I have a question. Thanks for a nice talk. So, so you did this mapping between the unitary operator to a state, right? So now I wonder, this could also be done in general for any CPTP map, I suppose. The Choi.
One has to be a bit more careful. So any CPTP map, okay, the operator acts on a state. So therefore, the operator which was a I'm saying this sort of very crudely. The operator which was a matrix of size nh cross nh, nh being the Hilbert space dimension, can be written as an nh square dimensional vector. Now, a CPTP map in general works itself on a density matrix. Okay, so the operator, if you want, so the operator itself, if you want to vectorize it and write it as a super operator and then act on this isomorphism of the state, that operator itself is an nh square cross nh. Is an nh square cross nh square cross nh square operator.
Yes.
If you then sort of want to think of that map as a state, it will be an nh to the power 4 dimensional state. So you'll need 4 copies of the system. I mean, that's not surprising because you're sort of evolving the density matrix. So you already have 2 copies to start with, and then you're doubling that. So yeah, that's the difference. But yeah, you can do that.
It becomes it becomes very large. But what about the statements that you have made here? So suppose I restrict furthermore to say Markovian log dissipative kind of thing. Or is it like just?
I don't know, because I don't even know whether these are good definitions of whether these are good entanglement measures for CPTP maps or not.
Okay. Yes.
Because if you have a CPTP map, it just means, in the most general case, you are dealing with a mixed density matrix,
right.
and then obviously these things are not good definitions of entanglement measures in there to start with.
Okay.
So.
So anybody has another question?
Thank you.